the fish tend to swim towards the anode, and so actually this is a good point of clarification. So in this presentation, we will be considering, you can kind of see, I don't know if you guys can see my mouse, but you'll see that we refer to the cathode as negative and as the anode as positive. Now this is actually something that I've learned on this project, is that anode and cathode is actually specific to the field that you are working in, which is kind of fun. So different fields actually will switch that and call, sometimes they'll call the cathode the positive. And so in an effort to kind of not be too confusing, you'll probably hear me refer to them as just positive or negative. But I will probably use the word cathode and anode. And so in this presentation, when I say cathode, I am referring to the negative voltage, and anode as positive. Negative or ground, electrical ground. So most power is transferred to the fish when the conductivity of the fish in the water are the same. This makes sense. It's just kind of a resistor network. And so we know when impedances match that is when maximum power is. So on that note, when electrical fish barriers don't work great in salt water, and this is because the conductivity of the water is significantly higher, and so you don't get nearly enough of that current through the fish, or voltage drop through the fish, to actually deter it. Fortunately, though, on this note, and we'll probably talk about this later, is that there's actually physical barriers to this fish as well. There's other things that step in when the conductivity of the water kind of fluctuates sometimes. So the larger the fish, the less the electric field needs to be for it to actually deter the fish. And so we can kind of think of this as a larger fish having a larger voltage drop across it. Whereas a smaller fish it'd be quite a bit smaller. And so you'd need more current to go through. And right now, pulse DC is kind of the state of the art for various different reasons. So one thing that is kind of interesting is when the fish get into this electric field, when it's strong enough, they will kind of non-voluntarily rotate towards the anode, and eventually start to drift that way, and then they'll eventually either depending on how strong the field is, they can either become unconscious or even death. So this is kind of a fun video. I don't know if it'll show very well over our network connection, but I'll try to show it. You guys have probably all seen something very similar to this. That's actually an example of what we're talking about with this kind of non-voluntary seizure as the field gets stronger, and you see that they've eventually just kind of. So I think it's kind of crazy. In that video, you'll see again. I'm sure all of you have probably seen videos like this before, but what's crazy is that you'll see you know, the anodes are actually right near, and then you'll see fish several meters away, you know, getting just involuntarily jumping. So a couple questions. You know, why do we need to create a simulation at all? Which is what this kind of presentation is focused on. And there's multiple reasons for this. Collecting experimental data is difficult. It's expensive. It's time consuming. We've got people that have to try to line up schedules across 3 to 4 organizations and travel, right? We've got complicated electronics, all these different things. So a second very popular reason is just simply verification of your experimental results against theoretical results. I had an advisor once tell me, kind of tongue in cheek, but at the same time, there's quite a bit of truth to it. And he said, you know, don't trust experimental results and don't trust theoretical results. Only trust them when they agree. And, you know, that's not always the case. We don't always have that luxury, which, but a lot of times, you know, that's, if we do have that luxury, that is obviously the best practice, because errors, you know, human error or whatnot can pop up on either side. And so, but once they agree, we can feel very strongly that those were correct. And so kind of lastly, and this has been really for Brandon Road a lot, is that, you know, fundamental changes, once something has been built and installed, a fundamental change is insanely difficult and expensive, if not completely impossible. However, with a simulation, it can be a matter of hours that something gets completely altered and tested to see what those changes would be. And of course, safety. Talking about pretty big electric fields here. So anytime we can keep people away from those fields and out of the water is really a good thing. So Romeoville had been doing a little bit of modeling before with a gentleman that is at ARL, and so he was unable to continue modeling, and so one of the first things that we did was start to build our own model and try to verify them against previous models that had been. So on this slide, we're looking at Romeoville. So over here on the left-hand side, we can see the conductivity of the water over time. And you see that the conductivity kind of changes drastically throughout the entire year. And this is mainly because of the salt that gets thrown down in the wintertime and then runs off into the river, and then starts to drastically increase the conductivity of that water. And so as we talked before, salt water or as water becomes more and more conductive, the less and less effective our electrical barrier is. However, fortunately for us, Asian carp do not really like the winter. They become very lazy. I don't know if hibernate is the right word. I don't believe that they hibernate, but they do not move nearly as much. And so actually wintertime, when the conductivity of the water starts to increase, is actually the time that we're least worried. And so that actually works quite well for our advantage. So through most of our models, we've kind of taken an assumed value for the water as 0.1 Siemens per meter. And then so for the soil, there was some resistivity testing done early on. I know Brandon Road has just finished up some, but based off that resistivity modeling, we've kind of come with we've decided on a bulk, kind of a bulk value of 0.004 Siemens per meter for the soil. So obviously, in reality, the conductivity of the soil is kind of a function of both space and time. I don't know if there's any geotechnical engineers in the house, but I know that they were probably losing their mind when I mentioned that this bulk value that we've chosen. Of course, a closer approximation would be a finite volume of the wet soil, so soil that's closest to the riverbanks, to the canal, and then as that gets out, right, it wouldn't be homogeneous. And that is actually something we're working on. I know Brandon Road has done some testing, and so if it's, there is always this question of, assumptions made versus, value added. So, we're going to talk about that exact subject actually a little bit more. So one thing that Romeoville has done is they've created these large bars for their electrodes. So they're 5-inch by 5-inch steel bars, and there's 8 of them that they electrically wire in parallel. So they can be seen as essentially one giant electrode. So I'm not going to get too heavy into some of the Romeoville stuff, because I want to make sure that we get to Brandon Road. But essentially, they have a wide array and a narrow array aimed at different types of fish. And you'll see that in our simulations, for most of these arrays, we're actually assuming one large electrode opposed to 8 separate ones electrically wired in parallel. And this allows for several advantages: faster computational time, better meshing, which gives more accurate results. And the truth is, we know that right at the electrode, that our results will vary from reality right at the electrode. But as you get farther and farther away, that's no longer, these 8 wired in parallel versus one large electrode are actually going to start to look exactly the same. And so we are most worried about near the surface of the water because so much energy is expelled right there at the electrode. And so for that reason, we know that we can kind of make this assumption, and we have shown against experimental results. So here's some results from Romeoville versus our model. So in one of their reports, you know, they've taken a boat right down the middle of the lock or several different places throughout the lock and collected data. And you see that for their wide array, they get kind of anywhere between 0.85 and 0.93 volts per inch. And our model was showing 0.87. And for their narrow array, they were picking up anywhere between, you know, around 2.5 to 2.6. Our simulation showing kind of very close to that. So I'm going to skip through quite a bit of this Romeoville connections. Basically, what you can see is they have one wide array here and then one narrow array here. Then they just have a redundancy here. Also, it's the same thing. If anybody is interested in some of these actual detailed design parameters, you can reach out to Dave or Kirk Sunderman. So what we see here is we're looking at the lock with here's our wide array, and here's our narrow array, right? And so for the wide array, our anode is held at 800 volts. And then for our narrow array, the anode is held at 2000 volts. And then for our cathodes, we're actually just doing, I saw there was a question there. I could not pick it up quite quick enough. But so then for our cathodes, they are just held.
What is the reason for the wide versus narrow array with respect to the effect on the fish?
So yeah, so we'll actually get into that a little bit. So maybe I need to speed up here, watching the time. But so wide versus narrow offer kind of two different ideas. And we'll see that at Brandon Road, we've actually kind of optimized it. So the wider the array gets, the larger the area is, the physically wider the electric field is. However, you're increasing the total area within those electrodes, and so the amount of energy to raise those goes up. With the narrow array, the advantage of it is that you can get a higher field value at a lower energy rate. However, the field itself is significantly more narrow. And so this is actually a great question for the biologist, which is kind of what we did. We said, you know, the question is how wide, you know, does that have to be for the fish to actually be deterred, right? So there's both a value and a width. So if there's a strong field, but the field itself is only like an inch wide, you know, kind of like a dog through an electric fence, it may just push through. you know, if they'll get a little sting, but it won't be enough to deter them, and they'll just push through, take the hit, and keep going. But if that field is held much wider, you know, as the fish try to go farther and farther, they just either eventually becomes just so discomforting that they'll turn around, or they'll just become unconscious or die. And so it's kind of a like everything in engineering, we're playing with our variables and trying to optimize for whatever we've decided optimization means. And so we'll talk about that at Brandon Road a little bit, because we actually did some studies there into that value. I'm going to start skipping through quite a bit of Romeoville here. I know, so I give a decent amount of talks to people that have no idea what I mean when I say barge. I know everybody in this audience is well aware of what I mean. But I like to throw this in there for people that eyes just glaze over when you start talking about barge versus no barge present. So this is something that will show up in Brandon Road. So I want to go over these physics real quick. So when there's no barge present, so right here we're taking a cross section through the canal is what we're looking at. And so right here, when there's no barge present, and you're looking cross section wise, we see that our electric field is nothing but a function of depth, and that makes complete sense. Hopefully, you know, the closer we are to these electrodes, the stronger the field is, and the farther away we get, the more and more it drops. So again, over here, we're looking, no barge is present in this video, or in this image here. So in this image here, we're looking, we've pulled a cross section lengthwise through the canal. And so when there's no barge present, we see that the electrons, you know, they just want to go from positive to negative. They want to find their ground. And so they want to take the path of least resistance, as we know. And so a vast majority of them, a lot of them, are just going to want to go straight across, because that gives them the least resistance. But something that electrons also don't like is each other. They don't like each other. So like a traffic jam, they will say, okay, it's getting way too full here, so I'm going to take this slight curve, and then slight curve, right? And this is how we end up with these nice little shapes that give us a field at the top of the canal here. So this would be the top of the water, where this is this would be the riverbed right here. And so when a barge does become present in the river over those electrodes, all different things start to change, because that barge is just really just a giant sheet of steel. And so it's a extremely high conductivity. So when we look lengthwise here, again, looking across the canal, when we look lengthwise here, now all of a sudden our field has has actually changed directions. And that's because a lot of the electrons have decided it's way easier for them to go up into this extremely high conductivity steel, go over, and then go straight down. And so you end up losing you end up with these kind of bubbles in the middle. However, you end up with bubbles here, but so much of your field now wants to go up towards that barge because of having such high conductivity steel, that this field actually becomes actually significantly stronger. It's just changed direction. So here, a lot of it is going really horizontal or parallel to the way you would assume a fish would be kind of swimming. Whereas here, it's going vertical. A whole bunch of the field's going vertical up and vertical down, which is kind of perpendicular to the way the fish would be swimming. So one of our first questions to the biologist was, does this matter? Do the fish actually care? And the answer is kind of, but for our case, no. So it does matter, except that it does take a higher field strength when it runs, when it's going perpendicular opposed to horizontal. However, the value that they've come up with, so the field strength value that they've told us that we need to aim for to prevent fish has kind of factored that in. So they've overestimated, so to speak. So in our case, the field is so strong going up and down that for as far as our fish are concerned, it doesn't matter that it changed direction. So now what's a much bigger issue for us, and we'll talk about this in Brandon Road. So sorry about that. So when we're looking cross section here, this is what we're really concerned about. And we know is a problem at Romeoville, is when this barge goes through, we see that, again, the steel is so highly conductive that, remember the field is kind of starting down here. And so instead of kind of bubbling out, it goes up. It wants to go up towards the barge. And you end up with these giant gaps at the top sides of the canal. And then when you're actually over the electrode, you end up with a gap right around the barge. A bit more here. And so this is just kind of a picture of what we're talking about here. And so again, when there's no barge present, we see it's just a kind of a uniform field across. But when a barge is present, those two gaps that we're talking about creates this little hole here that the fish can kind of get through. So we did quite a bit of study into this, and you find that kind of your area of most concern is about halfway between the edge of the barge and the canal. And you can see it drops by about 45% of the value. So whereas when there was no barge present in that area, across through these electrodes, you get a field strength of around 2.53. And so the biologists tell us 2.3 is kind of their number that they like to see. So 2.53 is, a little higher to make sure that we're hitting it. And so we see that it drops by close to 45%, so 1.4 volts per inch. And so that was a big talking point for Brandon Road, especially since at Romeoville, a lot of these barges are going straight through the canal. Not exactly. I know Kirk's actually shown me a heat map, and I know it's in our GIS map, but of the traffic of the barges, and so not all of them go right down the middle, but you know, some of them kind of swing over to the sides and stuff. So for Brandon Road, a lot of the talk was done about, hey, are these bottom-mounted electrodes really the best way, really the best design choice? And so we actually spent quite a bit of time talking about different ideas. And what we'll see is that that really, with some slight modifications, they really are the best design choice, because we just end up with too many drops in the field that are a big issue. So when we have vertical electrodes on either side of the canal, right? And I know at least everybody that's an electrical engineer in the room, I would bet all had the kind of first thought that I had is, you know, why aren't they just vertical like a giant capacitor? Why don't we just make a giant capacitor? And we actually did do the studies that the energy actually works out very similarly. So that's not really the problem. But but again, when there's a barge present, there's a huge issue. So when it's just a capacitor or vertical electrodes, they go, you know, instead of going straight across, right now the electrons want to go up through the barge and then back down. And so we end up with this huge gap below the threshold of what's needed to deter the fish. And so we tried going several other different design choices to try to mitigate that, or, you know, look at different options. And the truth is that we just there was just always bubbles that were or areas that didn't give us what we needed. Some of which were even a problem, right, when there was no barge present. So really, with some slight modifications that we'll talk about a little bit later, the bottom-mounted electrodes really do provide the best option. And so one really big advantage that we have at Brandon Road is that the depth of the water is significantly shallower than what is seen at Romeoville. And this is a huge advantage for us, right? Because the more water we add, larger resistor we have, and so the more energy that's needed to pump in to get whatever field strength is needed. So I believe, yeah, Romeoville was right around average 26 feet, whereas Brandon Road is much closer to 13 to 16 feet. So one thing we've also looked into and talked about with Brandon Road is Romeoville put in these giant, they call them parasitics. So they put in these giant sheets of metal kind of to the left and to the right, anode and cathode, because one issue that we're trying to mitigate is straight current. Unfortunately, those parasitics at Romeoville were not electrically connected to anything. And so when the electrons, sure that they'll see the metal and they'll kind of head over there, but they might, you know, hang out on the metal for a little bit, but the truth is the electrons want to get to their ground. They want to go to ground, so that they care actually much more about that than just a being on high conductivity. They like using high conductivity metal to get to ground, but if that metal isn't connected to anything, it's not serving a ton of purpose. And so one thing we've looked at Brandon Road is what we call parasitic zeros. And so kind of the idea of adding, so instead of one anode and one cathode, so one anode held at a voltage and then one cathode held at ground, electrical ground, which is 0 volts, actually holding several different, having multiple cathodes. So one anode with 2 to 3 or 4 0 volt grounds, with the idea being that it actually it kind of helps with the straight currents and with providing more places for those electrons to go. Because again, they want to get to ground, but they also, they want to take the easiest path, but they don't want to be surrounded by each other. And so what we've seen is that by doing this, we can actually kind of persuade them to go to the direction that we want. So one of the design ideas we've talked about with Brandon Road is about the width of the actual channel. So just like the depth of the water, right? The more depth, the more resistance. The wider the channel, the more resistance as well, right? Just more water. And so for Brandon Road, essentially from an electric barrier standpoint, no other things considered, the more narrow that channel is, the better it is for us. Again, just talking about the electric barrier. And so I think, so one of the design ideas is for Brandon Road to kind of funnel in near this electric barrier and then kind of funnel out to allow for for easier navigation. Because I know navigation is not a huge fan of having a super narrow channel for a long area. And so we've actually made a suggestion, talking with the biologists and with Brandon Road, of 6 volts per inch, and some of the people at Romeoville. And we can hit 6 volts per inch with a 110-foot wide channel, 15-foot depth, right? Held at 2,500 volts. And that puts the power requirements anywhere between 2/3 to 100% of what Romeoville is currently using. But they are getting around anywhere from 2.3 to 2.6 volts per inch. Now, anybody that's super familiar with Romeoville, you'll know that that they're starting to build many other barriers. And so I'm only talking about barrier 2A and 2B, if you're familiar with that. And this 6 volts per inch actually comes from the new barriers that Brandon Road that Romeoville is building. And they've decided that this is the target, the better target value to really prevent those smaller fish from getting through. It's a better value than the 2.5-ish that they have now. So so we talked a little bit about adding those extra 0 cathodes here, or grounds. And so one thing that Brandon Road is looking into is the idea of having one of them that can actually be either an anode or a cathode. So it can either have a voltage or be held at ground. And the advantage of that is that it would give us redundancy if needed. So as long as this is operational, this could be just held at ground. But if this, if one of these was to go out or there was an issue or maintenance or what have you, you would have redundancy there. And so you'd either have one anode with 3 cathodes or you'd have one anode with 2 cathodes, depending on the setup. And that's really just done as a redundancy idea. So here is, I hope this better answers the question than just my words. Talking about spacing of the electrodes. So a wide array versus kind of a narrow array. So here you'll see the anode and cathode are held at 15 feet, whereas here they're held at 40 feet. And for all of these, the same voltage is used. And so what we see is that assuming the same voltage, the same energy requirements, if we assume that, then the wider the electrodes get, you get this much wider field, right? But at a much lower peak. And then as they get smaller and smaller, you end up with the total max value goes up, but the width starts to decrease. And so what's not shown on this graph is actually what when you get smaller than 15 feet. And that's just that this actually eventually hits a kind of a critical value. So one thing that you can do is if it's decided that you need this really wide field, if you, instead of holding at the same voltage, if you were to increase the energy requirements, you could raise this to be even. And so the question becomes, how wide do you need the field so that the fish won't just push through, take a little zap and keep going, but at the same time, being able to kind of save on some of your energy requirements. And so talking with some of the different biologists about what those, kind of values look at, and the fish that are normal, their size, we've decided that the optimum value is 15-foot spacing of those electrodes. So here I'm going to talk a little bit about, a little speed up here, the slight modification to the bottom mounted electrodes. And that slight modification is the U-shape electrode opposed to just one bottom mounted one. And this is done to try to help with those gaps on the side. So this is what we've talked about, these gaps on the side being an issue here. And so as a barge gets closer and closer and closer to the side of the canal, you see that the field strength gets smaller and smaller and smaller, where it's almost zero. And Brandon Road will actually be up against the wall quite a bit. So this is kind of a problem. And so these U-shaped electrodes you can see actually mitigate that issue. So one thing that we discussed with Brandon Road is the idea of actually grounding the barge. And so from a theoretical standpoint, this is actually beautiful. It would solve almost every problem if the barge was to be electrically grounded. And we talked a little bit, just kind of got into the design ideas of like a traveling, using like a traveling kevel that could connect to the barge, right? And it would be a grounded cable. But the truth is, when you really get away from the theoretical beauty of it, like everything, so many things in life, is when the real world starts to happen, you realize that it's really just not a possibility from both practical and from a safety standpoint. So from a practical standpoint, the amount of current that would be running through that barge or through that that grounding cable would be extremely high, and so the size cable you would need to actually ground the barge is really not practical. And then the second issue being that these barges are not a perfect homogeneous piece of metal. There are several barges, connected and close to each other. And so if something was to happen where one barge was not perfectly electrically connected to the one next to it, one boat connected, and you'd get huge arcing, because then one would there'd be a huge potential difference between the both. So for both those reasons, we've suggested that that's not, although it's a beautiful theoretical fix, it's just not a possibility. We don't believe. So straight currents are quite a big concern. This is going to be the last topic I discuss. And so some of the simulations that we've done is this idea of if a deckhand is tying off to an individual that is up on the canal at the top of the wall. And so in our simulation, what we've done here is this little green block is actually a giant blob of salt water that mimics a human. And you can dig into some of the literature where human estimates on the low end are considered 300 to 500 ohms, and that's really on the low end. If there's some pretty serious cuts and stuff like that, because your skin is actually in the mega ohm range. But we have straight current. Although we want all the current to go to the ground, we do get currents that run. Will kind of drift up and down the canal and into the soil. And so, one question is, how far away does this barge have to be, such that if there was a rope that was connected to the barge and thrown up on to the ground, that the concern would be that the currents would run through this rope, through the person, into the ground, headed towards ground. And so for all all of our studies and simulations, we have assumed this to be a metal rope. And of course, we don't think that's what will happen, but we want to make sure we're looking at the worst case scenario, you know, such as maybe it's a normal rope, but maybe it's been soaked in salt water, you know, as it just sits there on the top of the deck. So then kind of our last recommendation for Brandon Road was talking about what to use for electrodes. And so you know, the corrosion of the anode is kind of a serious concern. Just some last other recommendations that were made was just about electrical safety as well. So I guess I was wrong, and I used my entire hour. So thank you for listening, Dave. I don't know if we have time for one or two questions maybe, or what we want to do here, but I'll turn it over to you at this time.
Does anybody have any questions? You can unmute yourself and ask, or you can head off. The next presentation will start at 10:20. Well, thanks, Kaylin. That was a very interesting presentation. Everyone else, you can. The next presentation will start at 10:20.